My name is Emmanuel Bimpo-Manfo. I'm from the University of Manchester, and I'm delighted to welcome you all on behalf of the organizing committee to our third talk in this third series of the seminars sponsored by the European VLBI network, focusing mainly on high-resolution radio astronomy. I just want to mention a few logistics ahead of the talk. You will be muted throughout this presentation, but you are invited to submit your questions that you have through our Q&A facility. Please, we emphasize that you use the Q&A facility to send in your questions, and you can submit your questions during or after the talk. Please, we ask that you keep your questions short and brief so that we can attend to many of the questions after the presentation. We apologize in advance if for some reason we are unable to attend to your question before the session ends, but we will try as much as possible to reach as many questions that we can. Now, I'll invite Javier Modon to kindly introduce our speaker for today, Leah Morabito.
Hello, everyone, and I'm very glad to welcome Leah Morabito to this EVN seminar. So Leah is a radio astronomer, expert in high resolution at low frequencies, in particular with the low frequency array, with LOFAR. Her field of expertise is in AGNs and coevolution of supermassive black holes with their host galaxies. And Leah started her LOFAR journey at the Leiden Observatory, where she did her PhD. And after that, she moved to Oxford, where she was a Hinds Fellow. And then she went to Durham University, where she's currently an UKRI Future Leaders Fellow and chair of the LOFAR High Resolution Working Group. She's also a core member of the LOFAR Survey Ski Science Project, member of the MIGHTY Survey, and she's involved in several other large projects. She recently won the Royal Astronomical Society Fowler Award for Early Career Achievement, so congratulations for that. It was quite amazing to see your name there. And for the last 10 years, she has been fundamental to developing the VLBI capabilities of LOFAR. She has been coordinating the group of people that has made possible that the LOFAR VLBI capabilities, the commissioning of all that observing modes, converting that into an actual working instrument, working and efficient instrument that is for benefit for the whole community. So now it's an instrument that everyone can use thanks to empower with the work of coordinating this very nice group. So welcome, Leah. It's very nice to have you here, and the floor is yours.
Well, thank you, Javi, for that very nice introduction. And hello to everyone out there. Let me just share my slides. Yeah. Okay. So thank you very much for that nice introduction, Javier. I'm very excited to tell you about all of the work that has happened over the last decade and what we're looking forward to in the near future. So the title of the talk is The Highest Resolution at the Lowest Frequencies. We're going to talk about the LOFAR view of the radio sky. And if you want a little bit more of a visual, if you're a little bit more of a visual person, just here's a little primer for myself. I am a radio astronomer. And I'm a radio astronomer because of the movie Contact, and I work on LOFAR. And I've been doing this for the past 10 years, working on getting this high resolution at low radio frequencies. So let's start with a LOFAR view of the sky. So this is not necessarily a very high resolution image, but this is 6 arcsecond resolution at 150 megahertz. This is a portion of the Elias N1 field. The orange color map on overlay here is the radio, then that's overlaid on optical. And so this is just from the LOFAR surveys collaboration. This is just an image to show you what the radio sky looks like. And you can see it looks very different to what you might expect from an optical image. And so there's a lot of information to be gained here when you go to radio wavelengths and to understand what's going on with these galaxies. So to give you just an overview of what we're going to cover this morning or this afternoon, depending on where you are, we're going to go through a little bit of the basics on the International LOFAR Telescope. We're going to talk about why we want to do high resolution at low frequency, so what is the value in it. We'll go through calibration techniques for LOFAR VLBI, some recent successes, and then finish up with future plans. So to start, the International LOFAR Telescope. So LOFAR stands for the low frequency array. This is a phased array that operates below about 200 megahertz. There's two bands. There's the high band antenna and the low band antenna, and you can see examples of these antennas, individual dipole antennas here. And these are collected into stations, and then those stations are spread all across Europe. You can see the locations of all the stations here on the map on the right. LOFAR has a very large fractional bandwidth and very flexible spectral resolution and a very wide instantaneous field of view. So the field of view using just the Dutch stations is about 20 square degrees. So I mean, that's incredibly large, which makes it a very efficient survey instrument. It also has multi-beaming capabilities because it is a phased array, so you can point the telescopes after you record the data in different directions on the sky. And it has flexible angular resolution because it has such a wide range of baseline lengths. Just to give you an idea of what these stations look like, this is the SuperTerp, which is a collection of 6 stations at the very heart of the array in the Netherlands. And so here you can see these are the HBA tiles antennas here. They're covered with this black tarp because they're a little sensitive to the weather, whereas the LBA, the low band antennas, are not so sensitive. And there you can see the ground screens for all of the dipole antennas scattered throughout this particular station. So in terms of flexible angular resolution, you can get that from just using different collections of antennas. And so here is on the left, you can see a figure that shows you resolution versus frequency for LOFAR using 3 different sets of antennas. So just the core stations, which are just the very close to the center of the array stations, and then the remote stations, which are just the rest of the Dutch stations, so up to baselines of about 120 kilometers, and then the international stations. And I've put here for reference on the plot a line that shows you what the ground-based seeing limit is for adaptive optics using optical telescopes. And so this shows you that when you start to use the international stations with the high band antennas, which cover the frequencies on the right half of this plot, you're really starting to beat what you can do with optical telescopes on Earth, which is just incredible. So if you look at just using the core and remote stations, this is quite a standard mode of operations for LOFAR. Just baselines up to 120 kilometers, you get about 6 arcsecond resolution at 150 megahertz, which is really nice because that's matched with surveys like the faint images of the radio sky at 21 centimeters, with the VLA, which has been kind of a workhorse survey for the astronomy community for a long time. So with that collection of stations, we've been carrying out the LOFAR 2-meter sky survey, and this just shows you kind of like what you can get with that kind of resolution. This is a collection of nice sources from the LOFAR 2-meter sky survey, and you can see the beautiful diversity of sources. A lot of these are active galactic nuclei, or AGN, that have these very large-scale powerful jets, but you can see we're also resolving individual kind of components of star-forming galaxies. So the LOFAR surveys, the LOFAR 2-meter sky survey has been processing data with just the Dutch stations, even though it's recorded with all of the international stations. And thus far, we've had 2 data releases. So Tim Shimwell, whose picture you see on the slide, has really been the driver of these data releases. And so there's been one in 2019 and 2022, and we're about 30%, that contains about 30% of the final survey footprint. And we're continuing to process as we go on. So this, again, uses the HBA. We're only processing the Dutch stations now. There's this wide area component of it, but then also looking at several deep fields, Lochman Hole, Booties, and Elias N1, and we'll come back to those later on in the talk. The nice thing about the LOFAR 2-meter sky survey is that there is multi-wavelength data, so the wide area is cross-matched with optical and IR. So if you are not a radio astronomer and you want to have radio data, you can cross-match between optical positions and then get the radio information for that source, which makes the cross-matching a little bit easier for you. The deep fields also have excellent ancillary data, so up to something like 24 photometric bands across the optical and infrared, and in some cases the X-ray. To give you an idea of where the LOFAR 2-meter sky survey sits in terms of other surveys, this shows you resolution versus frequency, and then the color is all of the sensitivities of the surveys at different frequencies have been scaled using a typical synchrotron spectral index, so that they're all on the same color scale. And then you can see the sky coverage of the survey, which is just how big that colored point is. So LOTS is doing really well in terms of resolution compared to other things at this frequency range. It's very similar in resolution to FIRST, and also much deeper than the FIRST survey, about an order of magnitude deeper, and it's much deeper than anything else at this frequency. The LOFAR 2-meter sky survey has been doing really well. There's already over 300 science papers using LOTS data, so it's really fantastic. So you can do a lot of science with just the Dutch stations of the LOFAR telescope. But we're here to talk about VLBI, so let's extend this now to all of the international stations. So with this, you get baselines of up to about 2,000 kilometers, which means you can increase the resolution by a factor of about 20. So 20 sounds like a big number, and that's impressive, but it doesn't really give you kind of a feeling for what the improvement is in resolution. So let's take this image on the top left here. You can see that there's some things going on there. It's kind of blurry. You can see there's colors, different colors. You can see there's shapes, but you can't really see what's going on. So if I increase the resolution of this image by a factor of 20, which is the same as going from the Dutch stations to the international stations, then all of a sudden you can see it's my dogs in my backyard. They're sitting on chairs. There's 2 of them. They're different breeds. You can see all of the kind of fine detail you want to know. You want to understand what's going on in this image. And that is exactly the kind of resolution improvement that you get by increasing your baseline lengths out to the international stations with LOFAR. So in terms of astronomical sources, what this improvement looks like is something like this. So this is actual data, and the GIF here is fading from 6 arc seconds to 0.3 arc seconds, which is what you get with the international stations. And these are all real sources, real data. To put that in context of optical information, what that means is that suddenly you're going from something. So here in these 3 panels, you have the optical underneath all of 3 panels. This is what you get with the LOFAR Dutch stations for this particular source. It's just a blob. You can't get any sort of information on what's going on morphologically with this source, but then you resolve it with the international stations, and all of a sudden you can see these beautiful galaxy scale jets, and you can really start to understand what's going on physically in this source. And just to really demonstrate the flexible angular resolution, here are a collection of 4 images of the same part of the sky in that Aleus N1 field that I showed at the very beginning. These images were made by Jurjen de Jong, who's a PhD student at Leiden, going from 6 arc second all the way down to 0.3 arc second. And you can just see the incredible range of information that you get. As you get to higher resolution, you start to resolve out the diffuse emission, but by imaging at intermediate resolution, so 1.2 arc seconds in the upper right hand corner here and 0.6 arc seconds, you can still retain some of that diffuse emission and see the different structures that you get on different angular scales. It's just really incredible. Okay, so that's showing you what high resolution looks like. So now let's talk about why we want to do it. So why are low frequencies important? So this image here shows you flux versus frequency, and on it I've plotted just a typical kind of like spectrum that you might expect from a radio AGN. So both at redshift of 0 and redshift of 2.5. So low frequencies are important because the synchrotron power law means that things are brighter at low frequencies, which means that you don't have to build as sensitive of an instrument to reach fainter populations. So you can start to probe down into more radio quiet sources, so fainter things than you could with high frequencies in a similar amount of time. It is the only way to measure low frequency absorption. So you can see the VLA bands, even for this redshift 0 sources, are just completely missing this turnover at low frequencies. It's also important if you want to study high redshift sources because, as you can see, the spectrum shifts over for high redshift. And so then you really need to go to the low band of LOFAR to be able to understand what low frequency absorption is happening. You just cannot get that at all with the VLA. And it's also very important to anchor spectral modeling to assess spectral aging, so the losses that you get at higher frequencies. And I'll give you an example of that in a second. And so what about high resolution at low frequencies? So great, low frequency gives you good information on what's going on about the radio spectrum, but why do you want high resolution in particular? Well, 90% of sources in lots are unresolved. So at 6 arc seconds, almost everything is a point source. And so if you increase the resolution, suddenly you're able to precisely identify the host galaxy. So here the white circle is about 6 arc seconds, and then the red is 0.3 arc seconds. And so you can see that for this collection of galaxies, if there's radio emission, you wouldn't necessarily be able to tell which galaxy is producing it if you just have that 6 arc second unresolved source. The other thing that you can do is you can actually understand when one source is more than one source. So this looks like it might be a wide angle tailed galaxy. This is a 6 arc second resolution image. But when you then image it at 0.3 arc second resolution, you can see it's actually 3 sources. You have a point source, you have an FR1, and you have an FR2 possibly, that are all, in this very small region of space, and they just look like a single source. This was classified as a single source in the original lot 6 arc second catalog, but we can understand now that it is actually 3 different sources. So to give you an example of why this resolution is important for understanding substructure, so why do you need to understand that? Here's a nice image of a high redshift galaxy. So this is at redshift 2.46, made by Fritz Feyen and using the HBA. And he took this image, which is just absolutely beautiful, and combined it with the HBA with LBA images and VLA images at gigahertz frequencies to get spectral aging maps. And so you can start to understand what's going on in this source in terms of how old the plasma is, which tells you something about the overall evolution of this source. So spectral aging is what happens. You start off with a radiosynchrotron spectrum, which is just a power law. And as the source ages, you get this high frequency turnover. And to be able to understand how much it's deviated from that initial power law, you really have to go down to low frequencies to be able to get an idea of what that initial power law spectrum was. And so the high resolution at low frequencies is really important to be able to do this. And you just cannot do this without the high resolution at low frequencies, because if you take, for example, the Dutch resolution, everything would be averaged across this source. And you wouldn't be able to understand the difference in all the spectral ages across this, for example, this radio lobe. Another thing you can do with high resolution at low frequencies is you can do brightness temperature identification of AGN. So for those of you not familiar with brightness temperature, it's not an actual physical temperature, it's just the temperature that a black body would have that produces the radio emission that you would see. And so you can measure your flux density per solid angle, which is equivalent to brightness temperature versus frequency. Using models, you can understand what the limit is for star formation. So anything in this shaded area would be produced by star formation. Anything above cannot come from star formation, and so it is associated with an AGN. And so at 6 arc second resolution at low frequencies, you can't tell anything. But if you go to high resolution, all of a sudden, things with detections above this limit, you know that there's an AGN there. The nice thing about this, so this is done at gigahertz frequencies, but at gigahertz frequencies, you need dedicated VLBI instruments like the EVN, and those have very, very small fields of view compared to LOFAR, where you get a few square degrees from a single observation and thousands of sources for which you can do this for. The nice thing about this is that the only observables you need for this are flux density and size information, and so you can just do this with your radio images with a high resolution at low frequencies. This figure just kind of gives you a nice summary. I haven't covered everything you can do with high resolution at low frequencies, but just to give you an idea of some different kind of science cases, you can study the morphology of radio loud AGN, so those AGN with those large scale jets, which have unprojected jet sizes of 10 to 100 kiloparsecs. You can reach the limit for AGN and star formation separation with the full ILT resolution. If you're interested in high redshift sources, with the full LOFAR VLBI resolution, you can start to measure the substructure of those sources. And if you're interested in nearby star forming galaxies, then you could look at individual star forming clumps at very low redshifts. So I'm not saying this is everything that you could do, but this is just a nice kind of summary plot for that. Okay, so let's move on to calibration techniques for LOFAR VLBI. The main challenge for LOFAR, regardless of what resolution you're trying to image at, is the ionosphere. And this is just a demonstration for you. The field on the left and the right here, this is the exact same field. It's two different observations. It's a 3 by 3 degree square field of view. And you can see that you have reasonably good ionospheric conditions in the right-hand side. And on the left-hand side is when the ionosphere is really acting up. So all of the point sources in here, they should be point sources, and they should be stationary because these are actually galaxies. So they should not be moving in the field of view. But you can see that the ionosphere causes things to shift position, to brighten, to dim. And the nasty thing is that they don't always do it in the same direction, in the same time. It's not like every source is going up in brightness and then down in brightness at the same time. Everything is happening differently in the image, in all the different directions in the image. And that's what really makes it very challenging to do calibration with LOFAR at any resolution, regardless of what set of stations that you're using. So for using the international stations in particular, these are the kind of data calibration challenges. So yes, the ionosphere is on this list, but there's other things that we have to contend with. So we need calibrator sources for our high resolution for the international stations. And those are kind of like Goldilocks calibrators. So they have to be compact and bright enough on subarc second scales. So you can't just take like the VLBI or EVN calibrators that at gigahertz frequencies and assume that they're going to have enough flux density on subarc second scales at 150 megahertz. So this was a big issue for us when we first started out. Data volume is just a logistical challenge. The data sets are 4 to 20 terabytes per observation, depending on whether they're compressed or not. The clocks, the remote and international stations are on individual clocks. So if you're familiar with VLBI, this is something that you also have to contend with. And then also the source characteristics. So because you have low frequency absorption, you can't always assume that the source structure is the same as at high frequencies, but the fact that there is source structure also contributes to our calibration challenges. So let's take just the calibrators first out of this. So to find kind of Goldilocks calibrators, we did a long baseline calibrator survey, the LBCS. So Neil Jackson has led this work. And it's complete now as of 2022. It covers the entire northern sky for the high band antenna, so that 150 megahertz frequency range. And this just shows you the sky density of sources. So this survey did multi-beaming with very small amounts of bandwidth and time to look at calibrator candidates and found about 30,000, there's about 30,000 sources in the final catalog. And what we found is that there's about one good calibrator per square degree, which is what it turns out you need to be able to calibrate in any direction of the sky. So that's great. We are extending this to the LBA, but it's going a little bit slower because we have to deal with reduced signal to noise in the LBA, and also you start to really be impacted by those low frequency absorption processes. If you're interested in the survey, it's all of the data is available on our lofarsurveys.org website, so you can go there and you can search the long baseline calibrator survey. Okay, so that gives us calibrators. So what do we do about the rest of this? So how do we deal with all this? So Javier, who introduced me, made this very nice figure, which I still use even a few years later, which shows phase versus frequency, and these are the contributions that different things have to your phase errors. So here you have the clock, which is linear with frequency, and you have the ionosphere, which is dispersive, and that means it's nonlinear with frequency. And so your phases can be dominated at LOFAR frequencies. They are dominated by the ionosphere. So clock values are actually quite easy to solve for because we know the behavior that they introduce into your phases. It's linear with frequency. We can just fit for this. But the really nasty bit is the dispersive delays from the ionosphere. And this is a direction dependent effect as well. So clock values, doesn't matter what direction you're looking at, the clock values are always the same, but the phase errors that are introduced by the ionosphere will be different in different direction in your fields, which means that you need to use those LBCS calibrators to calibrate your target field data with a calibrator in your field to start with. So to track the phase versus frequency behavior and really understand what the phase errors from the ionosphere are, you need the full bandwidth to be able to track this nonlinear behavior, or you need enough signal to noise that you can solve for phases in very small chunks of frequency and time. And then I just also want to point out, we also have to fight for signal to noise, because when you go to higher resolutions, larger baselines, larger UV distance, and you have resolved sources, then all of a sudden you have less signal to noise because you have less signal, because you have less, there's less flux density in your compact resolution elements. So I won't go into all of the details, but we have spent quite a few years developing a calibration strategy. This calibration strategy is based on using the LOTS processing as a start. So from a standard flux calibrator source, we get instrumental effects, and then the LOTS processing with just the Dutch stations gives us calibration solutions for the Dutch array. And then that feeds into what we call the LOFAR VLBI pipeline. So this solves for an initial dispersive delay in the field. There's a couple of techniques that we use that, like, we combine core stations, we coherently add them after their phases are corrected, and we phase shift and average to reduce the field of view when we're calibrating on that delay calibrator source. This helps us manage some of the data logistics. So this pipeline is available online. You can see the link there, and then there's also a paper describing this, and it uses LBCS to find those in-field sources. So Fritz Feyen and others have been also working on wide field LOFAR VLBI, so not just imaging individual sources, but finding then after the initial calibration, doing residual calibrations across the field and using that to, in a faceted way, get solutions for in every direction in the field, and then do a nice wide field imaging. So I'll just mention that the calibration uses LOFAR native tools, but we do borrow from some VLBI techniques to, for example, find the dispersive delay. So this gives you kind of the LOFAR VLBI pipeline and the wide field extension to it, give you kind of two modes for the LOFAR as a VLBI instrument. So the VLBI pipeline, you can image individual directions, postage stamp imaging. It's relatively quick in terms of computation. And then the wide field LOFAR VLBI is very good for deep field surveys. We're working on optimizing the imaging to get that computational cost down. And here you can see this is the Lochman Hole field, which Fritz Feyen imaged. And this is a Nature Astronomy publication from 2022. But you can see that this entire image, which is 7 billion pixels, is over 5 square degrees. The moon is here for reference, and that's just like an incredible resource for looking at all of these sources with high resolution. Okay, so let's talk about some recent successes. So the pipeline was kind of like first released in 2022. And with that, we had a special issue of Astronomy and Astrophysics with 11 new articles. This more than doubled the number of scientific results using LOFAR subarc second resolution at the time. And I just want to point out that most of those papers were led by early career researchers, which is really phenomenal. So this is really becoming more of a mainstream mode of the telescope. So that's really great. This is just a nice poster showing you some of the results, which we'll go through a couple of these just to show you what kind of science you can do with them. So I'm interested in active galactic nuclei, of course, and this is a very nice paper from Roland Timmerman, who's a postdoc with me now at Durham, looking at these rings in Hercules A. And so he took the LOFAR image that he made of this and combined it with a higher frequency VLA images to make a spectral index map. And that spectral information then helps you understand that these rings are consistent with the supermassive black hole, the active galactic nucleus at the center of this galaxy, turning on and off. So that was a really nice kind of paper showing you about the life cycle of AGN. Pranav Kukredi, who's now a postdoc in Germany, you looked at the source, which this background image here is the 6 arcsecond resolution image using just the Dutch stations, showing you old jets, but then at the very center of the galaxy, there are new jets that have started. And looking at these, he was able to use higher frequency information again to show that these jet components, these very young jet components, there's evidence for interaction with the interstellar medium there. If you're interested more in star formation, there is also a nice study by Naim Ramirez Olivencia looking at this merging pair of galaxies. So there is an AGN in one of these, but the other one is powered by a starburst, possibly triggered by the merger. And this is really showing you, like, you can see really like all these resolved components in this very nearby source. And that's really an incredible resolution that you need to be able to have at low frequencies to then get spectral index information with high frequency radio instruments. So most of the results I focused on have been from the high band antenna, but Christian Groeneveld is really leading the way, blazing the trail with the LBA. So here's a collection of images from 2022 of just very bright sources. And these images, are breaking the record for high resolution at, these are the highest resolution images ever made below 100 megahertz. And then again, you can use these to study the jet ages and conditions, as I've shown examples of before with doing spectral modeling, combining it with higher frequency information. Something near and dear to my heart is doing brightness temperature measurements of AGN. So this is a look at the AGN population in the Lachlan hole. So there were 940 AGN identified out of about 2,000 sources detected in the Lachlan hole from that image that Fritz made of it using brightness temperature. 160 of these are new identifications. So I chose this field because also we have other AGN identification methods, and so I can try to validate that, and that went pretty well. I think the thing really here to mention is that all of this was done from a single 8-hour observation, and that's really the power of doing this using brightness temperature at low frequencies with LOFAR to identify AGN, because rather than having to use many hundreds of hours to cover a field and get up to this number of sources, about 2,000 sources, you can really do this with just a single 8-hour observation because the field of view is so large. The percent of subpopulation, which are brightness temperature AGN, is listed here. So you have your radio galaxies, unclassified sources, and radio quiet AGN, and even some star forming galaxies turned out to have a high brightness temperature component. So this really implies that the radio quiet population have more than one radio emission mechanism present, because they're not all high brightness temperature. Like the radio quiet AGN are only about 32% high brightness temperature cores. They're not all high brightness temperature. They're not none of them are high brightness temperature. So there's really a mixture of radio emission mechanisms present in those populations. And this just shows you those sources on the radio star formation plot. Okay, so I'll just wrap up then with some future plans. So we talked about the LOFAR 2-meter sky survey, and one of the things I'm working on now is extending this to high resolution. So I mentioned that the LOFAR 2-meter sky survey takes data with all of the stations, but is currently only processing the Dutch stations. And so here's this figure again showing you where LOT sits in terms of other radio surveys. And by post-processing the data with international stations, we can then turn LOTs into a survey where the resolution is comparable to the Hubble Space Telescope Wide Field Camera, which is really just absolutely fantastic and just knocks any other radio survey out of the park in terms of resolution. If you want to compare it to other surveys, I think the highest resolution survey that's on this plot is the VLAS or VLA Sky Survey, and that's at 3 gigahertz. So the resolution of that is 2.5 arcseconds, so beating that by an order of magnitude. The area covered with VLAS will be comparable. The noise will be better, which means that you can reach a fainter population because because sources typically have a steep synchrotron spectrum, and so they'll be brighter at low frequencies. But we will have a much lower source density. And this is really driven by the fact that as we go along and do the survey, we're initially only going to select sources to do postage stamp imaging using the LOFAR VLBI pipeline, which is very computationally cheap. So only doing sources that are above 10 millijanskis to start with. So that is where that's why this sources per square degree is so much lower than VLAS, but we do plan to go back then and do wide field imaging once the computational cost for that does come down. And so then finally, give it a few years, but this source density will increase. So to give you an idea of what this looks like and what our plan is, this shows you the northern sky. These are all the LOTS pointings, and this shows you the priority of the pointings. So we're starting in this area here, which is the H-Atlas field, and then we'll continue along the strip of declination, hitting these areas where you have pink, because those are where we will have the Weave LOFAR survey. And then kind of filling in the area where we have SDSS coverage, which is the gray in the background, and then finishing up with the low declination. Just to mention that our LOFAR, our LOTS data release 1, which is kind of this area here, doesn't have international stations because when the survey first started, we didn't know it would be possible to do this calibration, and so we didn't save the data because the data sizes are so large. But there will be plans to go back and kind of fill in this area to make up those pointings out where there's no international station information. So the status of this is that we have all of the standard flux calibrators, the instrumental calibrators, almost all processed. We're working on really like the last kind of like 10 at the moment. And we have started on the target fields in this H-Atlas area. And we are doing the calibration in such a way that we will get initially everything that's above 10 millijanskis. We'll get a small image of it, and we retain the calibration solution so we can go back and do wide field imaging later to get a more even coverage of the sky. There's also the LOTS deep fields, and so we're working on all of these high resolution images of all of these. So you've already seen the Lockman hole, and you've already seen some results from LASN1 by Jürgen, but also Marco Bondi is working on the NEP, and my PhD student, Emmy, is working on the Booties field. And so we have high resolution images. It's all kind of like in a little bit different state. So Jürgen's about to submit a paper on LASN1, which will be really fantastic because that'll be much deeper than the Lockman hole image. And Emmy is just making the first images of the Booties field, full field. So that's really something to look forward to. And I just want to mention that because this is an EVN seminar, for the Lockman hole field, we do have an EVN eMerlin follow-up. Jack Radcliffe is the PI of that. And just to give you a comparison, so this was a single 8-hour observation for LOFAR, but to image all of the sources with the EVN and eMerlin that are detected in this image will take about 260 hours compared to 8. And then finally, also in collaboration with the Cosmos survey, we're looking at a low declination, the Cosmos field, which is low declination. So the beam is a little bit elongated, but it does provide matched resolution with the VLA at 3 gigahertz. And so this just shows you a very nice image of a source. So the background here is the VLA image, I believe, and then this is the LOFAR image in the contours. And then towards the future, so Philip Best and I are PIs of the large LOFAR 2.0 large program. So LOFAR is currently going through an upgrade at the moment, which will increase its back-end capabilities, making it a more efficient survey instrument. And you will also be able to co-observe with the HBA and the LBA at the same time. But Philip Best and I have proposed a LOFAR 2.0 ultra deep observation for the Euclid Deep Field North. So just over 3,000 hours in this field, using a dithering pattern to get kind of better coverage of this blue circle, which is the Euclid coverage, the primary Euclid coverage in this field. We will get about 2 microjansky per beam area averaged RMS. So it will be confusion limited at 6 arc seconds, but because we're doing this with 0.3 arc second resolution, then we won't be. The field of view finally will be 3.7 square degrees, and we expect to detect about 275,000 star-forming galaxies. So the sky density that we expect of sources in this field will be about 75,000 sources per square degree, which is just really incredible. That's comparable to things like the Hubble deep fields. So I'll just finish up by saying that sub-arc second resolution imaging with LOFAR is becoming mainstream, and we have a lot of plans for the future. But I just want to say thank you to the hard work to all of the people who have contributed over the last decade. So these are just collections of images of the LOFAR Long Baseline Working Group. And I do want to highlight, my PhD student, James, who's also contributed a lot to this group, and Matthijs van der Velde, who's a software developer working with me on the LOFAR VLBI pipeline. So I will stop there and happy to take questions.
Yeah, thank you very much, Leah, for such a wonderful talk, bringing the low frequency bit to the high resolution world of astronomy. So we have a couple of questions from our participants. So the first question is from Ilse. Ilse wants to know for the EHT, there is an effort to develop tools to make movies of a radio source. Would such tools help with the ionospheric calibration?
Oh, well, hi, Ilse. That's a good question. I think that's effectively what we do. So we are solving on very small time chunks when we solve for the ionosphere on the in-field calibrators. I'm not sure that making a movie would necessarily is really necessary, but I think in effect this is what we're doing. We just don't visually represent it, if that makes sense.
Okay. Yeah, and there's also another question from Agnes. Agnes wants to know, what impact do you think LOFAR 2.0 will have on calibration?
Yeah, that's another good question. So I think that LOFAR 2.0 will potentially make doing what I've just described here with the HBA possible with the LBA. And the reason I say this is because we really fight for every piece of signal to noise with the LBA, because the LBA antennas are about a factor of 10 less sensitive than the HBA antennas. And you're having to contend with worse ionospheric, not worse ionospheric conditions, but because the ionosphere is dispersive delay, it's much more, it contributes much more at the low frequencies. And so then you have issues where you're trying to get signal to noise to correct for the ionosphere, but the ionosphere is worse. So the idea is that if we can do simultaneous HBA and LBA observations, that you can then use the HBA to estimate what the ionosphere is, at least the first order effects, and then you can project that down to the LBA, and that hopefully that will correct it, provide enough of an initial correction that you can correct for any third order effects of the ionosphere and be able to actually calibrate at LBA frequencies. So, in theory, this should work, but until LOFAR 2.0 comes online and we have the opportunity to play around with the data, I think we won't know in practice how far we can push this. But I think our expectation is that it will make it possible to do quite a bit more with the LBA than what we can currently do, which is really limited to bright sources near the center of the field of view.
Right. Yeah. Thank you very much. There's another question from Sina. Sina wants to know, what's the typical brightness temperature value for AGN and for star formation in LOFAR?
So I think we can go back to all the way back. Actually, I'm not sure I have I don't really have a picture of what the typical brightness temperature is. But you can check out this paper, Morabito et al. 2022. It's in monthly notices. Or you can look at Fritz Fein also applied this technique to Heilergs and Lochmann. And so that's there. But you can see that, so here's your flux density per solid angle. And I think the limit at LOFAR frequencies is about 10 to the 5.5. But this depends also on a little bit on what synchrotron spectral index you assume, what the redshift of the source is, and what the electron temperature is. So because it's dependent on what this model for your star formation is, there's a couple of parameters there. So generally the limit is about like 10 to the 5.5, I think, at LOFAR frequencies. And then things distribute above that. Here you can see I've just actually plotted flux density per solid angle. I haven't gone and converted it to brightness temperature, but all of these numbers are available in this paper, and then also you can look at Fritz's paper where he looked at a sample of Heilergs, but I mean that's for a particular sample, population, whereas this is for the general population.
All right, thank you. And there's another question from Ionis, who is asking, concerning the phase calibration, do you employ something like the frequency phase transfer technique that is used in higher frequency VLBI observations?
Well, okay, so we started out by doing fringe fitting in apes. So for, let's see. Yes, so because we were really struggling for signal to noise, we tried to do fringe fitting in apes. The problem is that dispersive delay, so apes, the fring in apes assumes that you have a linear dependence between phase and frequency and not nonlinear. And so you can do things where you divide your bandwidth into smaller chunks and assume it's linear across that. And so that's something that Eskil Varenas did for M82 and ARC220 and was quite successful at. But it depends a bit on your ionospheric conditions, like how much you can get away with. So we started out by using fringe fitting, and in some cases, what we would do is we would estimate what the total electron content was, so what this dispersion factor is, and then correct it so then your phases are linear with frequency, and then you can use like the entire bandwidth when you go in and do fringe fitting. But we have actually just moved to solving for the phases in very small chunks of frequency and time. So we have, as we've progressed through the last 10 years, the primary calibration, like all of the calibration steps that happen before you get to the point where you're solving on an in-field calibrator have improved, including at the station level, the station calibration. And all of these kind of have a knock-on effect. And so the better off you start your delay calibration in field, the easier it is to use smaller frequency and time chunks. We do still, within these solves, which are more traditional gain calibrations, we still do use things like smoothing and frequency and time, which is a bit kind of like fringe fitting, where you are extending your solution interval to fit something over a larger period of time, but not quite the same. I'm not sure if that answers your question, but I'm happy if you want to chat about this more. I mean, drop me an email or something, or I mean, you can read the paper. Yeah, we have started from fringe fitting and we've moved on as we've understood the system better to some more tailored techniques using LOFAR tools.
All right. And there's a question from Eduardo. Eduardo wants to know, what about threats or challenges like satellite constellations or error generators like windmills in the LOFAR 2.0 era?
I'm not really sure. I mean, with the HBA, we already have to avoid some parts of the bandwidth because of RFI from things like digital auto broadcasts. I'm not sure if satellites, I'm not sure how much of an impact that would be. I don't think it would be very large. Yeah, I'm not sure really how to answer this question. We haven't really seen impacts now, and I don't know that LOFAR 2.0 will really change that much. I think we'll just have to kind of wait and see. That's not a very satisfying answer, I'm sorry, but I'm not sure I really know more than that.
Right. And a question from Francesco. Francesco says, hi, thank you very much for the nice talk. I missed something. Are lots HR data available also partially and calibration survey data?
Right. So LBCS is available now. So you can go to lofarsurveys.org and you can get all of the long baseline calibrator survey information. Just to note that there is no flux information for this. So if you read the LBCS paper from 2022, Jackson et al., you can see that there are some ways you can estimate flux density of these sources, but it's not included in the survey. Lots HR data is not yet ready. So we are just starting processing the target fields. And so that data we don't expect a data release for, another good, probably 12 to 18 months. So we're working on the H-Atlas field at the moment, but we have just started that, and we're in the midst of processing the first few pointings. And so we want to get like a good chunk of Sky before we have an internal data release for our collaboration. And then there will be, of course, a public data release after that, but it's not available yet.
All right. And there's also a question from Anton. Anton is asking, regarding the AGN population in the Lockman hole, the diagnosis is based on the brightness temperature. Is there any information on the compactness of these sources that confirms this diagnosis?
We can measure their sizes, and there will be a paper coming out that measures the sizes, but we do use size information to calculate the brightness temperature, because it is actually, so to calculate brightness temperature, actually what you do is you calculate flux density per solid angle, and then you convert that to a brightness temperature. But in this paper, I just measured the flux density per solid angle. But to measure that solid angle, you have to know what the size of your source is. So there's a lot of information in this paper about how I validated that these are actually AGN. But I think that and I've been rather conservative in some of the assumptions and estimates that I've made here. I think that we can do better than this, and I think that requires forward modeling the problem. And we have the very nice situation where we have the information at 0.3 arc seconds, but also 6 arc seconds, and so you can do a very nice job, like forward modeling the whole problem and then trying to match your AGN plus star formation models to both the high resolution and low resolution. And I think that's going to be a better way to do this. But it's very complex to do that. And so that wasn't in this first paper.
Right, thank you. So Leon had a second question, but I just wanted to give other participants the opportunity for their question to be heard. So the second question was, can you comment on the polarization results and status with LOFAR, like international LOFAR station?
Yes. Okay.
Or secular? Or
yes. So we are working on it. I am not the expert on this. Vijay Mahatma is doing quite a bit, and looking at 3C sources. There's also some results from looking at the LASN1 field, but that I've been showing from Urian. But we are still trying to work out the polarization calibration for the high resolution. So it is polarization calibration for using just the Dutch array is kind of understood. And so there are a couple papers out on that. So there's a VLOTS paper, and then there's also an RM grid from Shane O'Sullivan. But we are doing extra calibration on top of what we use for the LOTS survey. And we are still working out that all of the polarization calibration is being done correctly. And so we don't have any results to show for that yet. But it is an ongoing area of development.
All right, thank you very much. So just to mention, Eduardo, I think your question, the second bit with satellite, Leah mentioned that she didn't have much information on that, but kindly, thanks to Ilse, there's a link to a paper responding to that. So I think the paper detects, that's LOFAR telescope detecting Starlink satellites radiation between 110 and 188 megahertz. So please, yeah, I think satellite will definitely have some consequence. So do check out that paper for more information. Yeah, so, well, okay, well, I do this, just, okay, we've got 2 minutes. I'll take just this last question and then we just move on to the end of it. So a question from Cormac. Cormac says, how well can you calibrate the array in the absence of the Dutch stations, that is observing with only the 14 international stations?
Yeah, actually, we can do that fairly well. So yes, if the sources are bright enough. So we actually have started, when we first started this, we started by calibrating the international stations first and then calibrating the array inward. The way that we've constructed the calibration strategy is that we apply the Dutch information and then we go out to the international stations and calibrate those. But that means that there is a bit of a disconnect between what you're doing for the Dutch stations and what you're doing for the international stations. When we first started this, we did a lot of kind of like verification and checking that, like, okay, we know we can do it, apply the Dutch information and then go out to the international stations and include them. But we have also tried to do it the other way around because we wanted to make sure that we ended up with the same result. So we did a lot of testing to understand that this was possible, at least on bright calibrator sources. And the answer is that yes, it is. So we use all of the telescopes now because we want all of the information and we want all of the collecting area, as much collecting area and as much signal to noise as we can get. But we have verified that you can calibrate the international stations on their own, because I mean it's critical to understand that you're not just propagating models out to your international stations and getting something that is nonsensical or made up.
All right. Thank you very much. We are just on the hour, so apologies to everyone whose question was not being mentioned or read out. It's just that we've run out of time, but I hope you can always connect with Leah via email or some other means of communication to just get your questions and conversations and collaborations going. Yeah, so I'll hand over to Benito now to give us any final announcements or stuff.
Thank you, Manuel. Just some 3 quick announcements. We already scheduled the following EVN seminars. This will be the last one before the EVN symposium, actually. And then on 17th of June, Monday at 10 a.m., same hour as now, we will have Ross Burns talking about masers and all the campaigns that they've been doing in the last years with the collaboration to trace and trigger maser and transient activity there, especially in bright flares. And then with that, we will lead into the EVN symposium that will happen in Bonn in September. You can have more information in the website and through the QR code. The registration is open and the submission for abstracts too. And then at the end of September, beginning of October, we will have the ERIS school, which is a really good school to learn about radio interferometry, touching different observatories and different data reductions. So if you want to learn how to analyze radio data from LOFAR, EVN, other instruments, this is a perfect school for that. And the registration is open until the 10th of May. So you still have like 10 days to apply for that. And I think with that, we kind of finish the seminar here. Thank you everyone for coming and for Leah to do a great talk on this one. We'll stop.